Good evening, everyone. Welcome to ICTS Vigyan Adda talk today. I'm Rukmini, Faculty of Mathematics at ICTS. Um, I would first start with a few words about ICTS. ICTS is a research institute and with uh, two other mandates. Other than research, we have programs and outreach. And this Vigyan Adda is part of our outreach program. It's meant for undergraduate students mainly. So today, it's a great pleasure to introduce Professor Riddhipratim Basu, who is our today's speaker. Riddhipratim Basu is a probabilist currently working at ICTS. He was educated at the ISI Kolkata and obtained his PhD from the University of California, Berkeley. Subsequently, he spent 2 years at Stanford University before joining ICTS in 2017. He is interested in various aspects of probability theory and its applications, including models of random growth, random graphs, and interacting particle systems. So today he'll be talking about some tales of universality from the world of probability. Over to you, Riddhi. But before that, I just wanted to say, if you have questions during the talk, please put it in the chat box. Riddhi will also stop for questions sometimes. After the talk is over, so during the talk, it will be questions from the chat box. After the talk is over, longer questions will be, you can unmute and you'll be unmuted for your questions. Okay, over to you, Riddhi.
Yeah, thanks, Rukmini. Yeah, it's a great pleasure to be speaking at this platform, and I thank Rukmini and Anupam and all the other organizers for giving me this opportunity. So let me share my slides. Okay, then I can start. Okay, so as Rukmini mentioned, I'll be talking about some tales of universality from the world of probability. I should mention at the start that as this talk is aimed at undergraduate students, not necessarily specializing in mathematics, I will not be assuming any background in probability or statistics that you might have beyond what one would learn in high school. So if among the audience, if there are people who have specialized in probability and statistics, most of the talk would be rather elementary or boring to them. So I apologize in advance if some such person is in the audience. Okay, so let me start. So before talking about universality, let me start with a very basic premise. This is kind of one of the most fundamental premises of probability and statistics. So, in real world, we always deal with noisy observations. So we have a set of noisy observations and we want to recover the signal. We want to somehow estimate the signal and eliminate the noise. Okay, so what is a basic model? A very easy elementary model for this is that I have some quantity mu that I want to observe, but during the process of observation, there's some error creeps in. So what I end up observing instead of mu, I end up observing this random quantity xi, which I model as mu, which is the quantity, the signal I want to observe, plus epsilon I, where epsilon I is the error. So this is, and then I want to recover mu from these xi's. Okay, so this, how to do this? We quite intuitively know how to do this. I don't know if students these days still do these things, but when I was in high school, we would do this in classes 11 and 12. We'll do this practical experiments in physics, and then you'll have to sort of verify lots of natural laws and all. and sometimes you have to estimate the value of acceleration due to gravity and things like that. And what we will do is that we'll take lots of observations and we'll take average. So that's precisely what we were trying to do. So the observations are typically noisy. There will be some noise, but we want to actually recover the value of the signal from those. And what we used to do, we'll just simply take the average. So we want to estimate mu, and as an estimate for the mu, we'll use this quantity mu hat, which is the average of xi is simply summation xi divided by n. Okay, so this is something that is very intuitive, and we all do this in practice. But what is the theoretical basis of that? What guarantees that this mu hat that I gotten from my samples xi by taking an average is actually close to mu? Okay, so of course it will not be true always. So we'll need to make some assumption on the errors epsilon I. So what one typically assumes about the errors is that they are independent. So different observations, there's no sort of systemic error. So all the errors epsilon I in the ith observation, they're independent across I, and they're also identically distributed, meaning that we assume that the errors come from some distribution which does not change with the observation. And also we assume that there is no bias. It's not like the error will always be positive or not like error will always be negative. We assume that the average value of the error is 0. Okay, this is a natural assumption. If there is always some positive error, then we can't expect that the average will be will actually be close to the value mu that we want to estimate. Okay, so what is the theoretical guarantee under these assumptions? It's a result that many of you should be familiar with, although you might not have seen it framed exactly in this way. But this is called the law of large numbers, which says that for a sequence of independent and identically distributed random variables x1, x2, and so on, with mean mu. So remember, my xi was mu plus epsilon I, and epsilon I has average 0. So xi has average mu. Then this classical result from probability theory tells us that the average of xi, the first n elements of this sequence, as n goes to infinity, as n becomes large and large, they converge to mu. Okay, so of course, notice that the left-hand side is a random variable, whereas the right-hand side is a constant. So we have to specify what it means for a random variable to converge to a constant. So I don't want to get into the technicality, but so if you're familiar with this terminology, then I can say that the left-hand side converges to the right-hand side in probability or almost surely. If you do not know what it means, don't worry about it. The point is that as n becomes large, with very large probability, mu hat, which is the left-hand side, the sample average, is indeed close to mu. So the chance that the left-hand side minus the right-hand side is large becomes smaller and smaller as n gets larger and larger. That's basically what it means. Okay, so this is the law of large numbers. But now, okay, so that gives us some justification of why this averaging procedure is the correct procedure. But the next, the result we talked about, law of large numbers, says something about as n goes to infinity. Okay, so in practice, n is never infinite, right? N never goes to infinity. It's just some large number. So also, in practice, you need to know how large this n has to be, so that your estimate mu hat will be within some error tolerance of the actual value mu with large probability. So you want to know what is the value of n I need to choose so that my mu hat with probability 0.9 will be within 0.01 of mu. So these are kinds of questions that you want to answer. Okay, so if one wants to answer these questions, usually certain additional assumption on the on the errors will be required. So previously we just assumed that they are identically distributed and independent, which we'll just call IID from now on, and they had mean 0. And now we have an additional assumption which says that they also have variance 1. So if I look at the square of epsilon i's, so epsilon I squared, and I look at the average of that quantity is 1. Okay, I mean 1 is not very important. You can just assume it to be some constant, but for concreteness, let us just assume it is 1. And then we can give some amount of control of the difference between the sample average and the population mean. Okay, so this is a famous result. Probably is not wrong to say this is the most famous and fundamental result in probability theory. It's called the central limit theorem, which says that the setup is as before. So now we have the sequence of independent and identical distributed random variables xi with mean mu, and the second assumption is that now they have, I'm assuming that they have positive and finite variance, which I call sigma square. And under that assumption, then if I look at the sum of xi, then subtract n times the average, n times mu, divided by sigma, which is the standard deviation, times square root n. Then it converges to the normal distribution, which, if you are a student of any kind of quantitative science, you must have seen some version of this result, or some version of the Gaussian distributions or normal distribution somewhere or the other. So again, don't worry about what it means to say it converges. There is a notion of convergence of a random variable, which is known as convergence in distribution. It's not going to be particularly important for us what it exactly means. But from a practical point of view, you can think of the following. So if you look at the left-hand side, it's a random variable. If you draw samples from this distribution and plot a histogram, again, if you are doing any kind of quantitative science, you must have seen this before. So how to draw a histogram of a given set of data, and then that histogram becomes closer and closer to the probability density function of the normal distribution. I'll show you what exactly means in the next slide. But before that, let me tell you that this theorem actually goes back a long time. So the first instance probably that is recorded is by Abraham de Moivre in probably around 1730s. Although he did not quite phrase it that way. Normal distribution is also often referred to as Gaussian distribution. So it was formulated later in 19th century by Gauss and also by Laplace. But de Moivre already had a formula for the normal density, although he probably did not recognize it as a distribution as we do now. But he already had this convergence when the xi's are 0, 1 random variable. They're like a coin toss random variable, which takes 0 with probability half and 1 with probability half, things like that. And this was rediscovered by Pierre-Simon Laplace around 1810, probably. Again, he also did it for where xi's are Bernoulli random variables. Finally, a more general version, which is closer to the version that is stated above, is probably first stated and proved by Alexander Lyapunov around 1900. So it has a very old and rich history, and it is one of the most fundamental result of probability theory, and you can see why. So the sums of independent observations are pretty much everywhere in every kind of science. You will encounter those, and this result gives you a way to say how those things behave as n becomes large. So if you have not seen what is the Gaussian distribution before, this is what it is. So a Gaussian distribution is simply a distribution where I have a random variable capital X, and the probability that this capital X is less than or equal to some fixed number small x is given by the integral of the probability density, which is given by this 1 over square root 2 pi sigma I power minus x square minus x minus mu whole square by 2 sigma square. Again, the formula is not very important, but this bell curve you must have seen before. So this is mu is the mean, and this so this is essentially the limit. So when I said like limit of the histograms of samples drawn from the distribution of summation xi should converge to this. That's what I meant. So this is the probability density function, and so it puts mass 34.1% between mu and mu plus sigma, 13.6% between mu plus sigma and mu plus 2 sigma, and so on. So this is the famous bell curve, which I'm sure all of you have seen before. Okay. So central limit theorem explains the ubiquity of this normal distribution. Why do we encounter this normal distribution everywhere? And so coming back,
Professor
yes.
Riddhipratim, we have 2 questions related to the first 2 slides. Would you like to take?
Yeah, we can go and take those questions. Can you?
Yeah, I'll read it out. So first question is by Ahatra. He's asking, what is meant by identically distributed xi's, and is xi uniformly distributed?
No, it's not uniformly distributed. What I mean by identically distributed is that x1 and x2, their distribution does not change. So remember, these xi's are random numbers. No, so they are not fixed numbers. So they're, it's, I can give you an example. Say xi can be 1 with probability half and minus 1 with probability half. Okay. So what I mean when I say that these xi's are identically distributed, I mean that this distribution of x1 and the distribution of x2 and the distribution of x3, they are all the same. It does not change from I to I. Okay, so that's what identically distributed means. So it is not going to be like x1 has probability half of being plus 1 and probability half of being minus 1, whereas x2 will be probability 3/4 of being plus 1 and probability 1/4 of being minus 1. So in that case, it will not be identically distributed. So for our purposes, they will be identically distributed. So for all I, the distribution of xi will be the same. Okay, so what was the second question?
The second part of this question was, is xi uniformly distributed?
Oh no, so they are not necessarily uniformly distributed. So they can have any distribution as long as the mean is equal to 0 and variance is equal to 1. They don't need to be uniformly distributed. So for example, I said that xi could be 0 with minus 1 with probability half and 1 with probability half. It could be minus 1 with probability 1/3, 0 with probability 1/3, 1 with probability 1/3. It could also be like minus 1 with probability 1/4, 0 with probability half, 1 with probability 1/4. So it does not have to be uniform. It can be anything as long as it satisfies those two conditions, that the average is 0 and the square average is some fixed number.
Actually, this relates to the second question by Rukmini. So she's asking, do you need average of epsilon I to be 0 in the central limit theorem?
No. So if you let me go back to the statement. So if you see the statement of the central limit theorem, there the average is not assumed to be 0. So I assumed the average to be 0 when I was looking at this noisy observation model. This xi equal to mu plus epsilon I. But if the average there was not 0, I can simply absorb that average inside mu. So when I'm talking about the central limit theorem, I just assume that they have some mean mu. It does not have to be 0. Okay.
Okay.
Was there any other question?
That's it.
Okay, great. Okay, so coming back to the original problem, how we want to determine how large n should be. So again, do not worry about what is specifically the meaning of summation xi, this mu hat. Okay, so if you go back here, you will see that the quantity in the left hand side, it's simply square root n times mu hat minus mu. Okay. So in the previous definition that we had, so remember summation xi was n times mu hat. So this quantity in the numerator is n times mu hat minus mu, and I divide by square root n times sigma, which was sigma was equal to 1 in our original assumption. So this quantity in the left hand side is simply square root n times mu hat minus mu. So what convergence in distribution means is basically the following. It tells you that square root n times mu hat minus mu, probability that is bigger than equal to x, or probability that is its absolute value is bigger than equal to x, converges to the same probability for the normal distribution. Okay, which is the integral in the right hand side. So of course, if I want to be more if I want to write one more step, I would write the integral from x to plus infinity, which is the probability that mu hat minus mu is bigger than equal to x plus x by square root n, plus the integral from minus infinity to minus x, which is the probability that this is less than equal to minus x by square root n. But the integrand inside, the density is symmetric around 0. So I can simply replace the two integrals by 2 times one of the integrals. So this is what the probability is. So remember, so what does this mean? It means that if your x is something fixed, x is some fixed large number, say x is 3. If x is 3, then this quantity is something like 0.006 or something like that, the quantity on the right hand side. So the probability that mu hat minus mu is bigger than equal to 3 by square root n would be quite small if n is large. So what it means is that once I fix a tolerance limit, I can get an estimate of how large my n needs to be from the central limit theorem. Okay, and the important part is that it does not matter how my errors were distributed, as long as they satisfied the condition that the average error is 0 and the square average error is 1. Okay, so that is the important part. So I did not need to know anything about the specific way the errors are distributed. I need to only know their average and square average. Okay, and that the fact that they are independent and identically distributed. So that is the most important part of the central limit theorem, and this is an example. This is the most well-known and well-understood example of this phenomenon called universality. So maybe it's a good time to see if there are other questions, because this is kind of the main theme of the talk. So it would be good to have everyone clear in this aspect. Are there any more questions, Anubhav?
Yes, there is one question from Shinjini. She's asking, what happens when the mean of the distribution is not defined, as in Cauchy's distribution?
Yes, that's a very good question. So in that case, of course, central limit theorem does not hold. So remember, my central limit theorem already assumes that the variance is finite. So of course, if the mean is not defined, like in Cauchy, then the second moment or the variance, they will also be not defined. So central limit theorem does not hold in those cases. So you do need to assume something. So as I don't know if all of you are familiar with the Cauchy distribution. The Cauchy distribution is a distribution whose probability density function looks like something 1 by 1 plus x square. So it is decaying to 0 very slowly. So for such distributions, central limit theorem does not hold. You need to have certain control on the decay, which is given by this finite variance for the central limit theorem to hold. I hope that that answers your question. Was there anything else?
There is another question by Ahatra. Is there an intuitive explanation of how the central limit theorem is working?
Okay, so again, a very good question. So one thing you can check is that if you look at the left hand side here, it's easy to check that the left-hand side has mean 0 and variance 1. Okay, so each of the xi had mean mu. So summation xi has mean n times mu. So the mean of the left-hand side is 0, and you can calculate the variance by the standard formula for sums of variances of independent random variable. If you have seen such things, so the variance is going to be 1. So the fact that this quantity will be something, something as n goes to infinity, this quantity, if it converges, that it will converge to something with mean 0 and variance 1 is not surprising. But it is not so clear a priori that the limit it converges to will be Gaussian. Okay, so that that comes from the calculations. And also, I mean, you can think of this as some kind of a fixed point theorem if you have seen those. So this is also not completely unrelated to the fact that the density of the Gaussian distribution is invariant under Fourier transform. So you can think of this quantity as some kind of a fixed point theorem. So we know, if you have seen such results, so there are many fixed point theorems where you iterate the same procedure, eventually you converge to the unique fixed point of some function. So you can, in principle, think of central limit theorem. So I'm just looking at average of these smaller and smaller quantities. So remember, each of the xi's are xi minus mu. If you look at this xi minus mu, this is some random number with mean 0 and variance 1. So this is an order 1 quantity. So when I divide by square root n, it's some very small quantity. So I'm looking at a very large sum of large number of small quantities. And I'm aggregating this large number of small quantities, and eventually it converges to some distribution which satisfies certain fixed point equation. You can think of central limit theorem. You can think of intuitively central limit theorem as that. Okay. So was there anything else?
That's it.
Okay.
So suddenly there is another question.
Yes.
Sachin is asking, as the Gaussian formula is a little complex formula, how the Gaussian distribution formula may have come for the first time by Gauss, I believe.
Okay, so again, I'm not someone who specializes in history of mathematics, but I specifically did look up this yesterday. So it turns out that the Gaussian formula probably was first derived by De Moivre in 1733, 1735, something like that, where he was trying to calculate the limit of binomial probabilities. So you toss a coin n times. You toss a fair coin n times, and you look at what is the probability that you get exactly n by 2 plus x times square root n many heads. For binomial, you can write this formula explicitly, and then you can simply try taking limit as n going to infinity. So as far as I understand, or as far as Wikipedia tells me, it seems like that is the first instance where this Gaussian density, this e power minus x squared over 2, this formula was first written down. It's not clear if De Moivre actually realized that this is a probability distribution. That probably was first realized by Laplace. But Laplace also came to this formula by trying to compute the limit of binomial probabilities. So this is probably how the Gaussian density, the formula for the Gaussian density first was derived. But again, I'm not a history of mathematics person, so I don't really know. My knowledge here is purely from Wikipedia, so I can't really guarantee the veracity of what I just said.
So there's another question by Srinivasan. He's asking, the sum is bounded above by the maximum and below by the minimum. Why this inequality was not considered for the partial sum initially? Any idea? Again, I think it's like history of mathematics. Yeah.
So first of all, maybe this is not, maybe we can come back to this question later in the talk.
Sure.
not really the time to answer these questions. We'll come back to this at the end of the talk. Okay.
Sure.
Okay. So let me continue with this. So we saw this example of central limit theorem where the limit did not depend on the specific of the distribution. So you look at this expression again. So mu and sigma, they are specific to the random variables xi. But the fact that if I center by some constant times n, scale by some constant times square root n, then it converges to the normal distribution with mean 0 and variance 1. So this n, square root n, and normal, these three facts are universal. They do not change. If I change my random variables x, mu can change, sigma can change, but the fact that the linear growth, the growth is linear, it's the mu times n, the fluctuation is square root n, and the limit is normal. These three facts are independent of the individual choices of xi as long as they satisfy that the mean and the variance are finite. So this is an example of universality. Okay, so this n, square root n, and normal, these are universal as long as my individual xi's are 0, 1, have mean 0 and mean and variance finite. Okay, so this is, this term originally was coined by physicists, so it's not easy to define what it means. But I mean, the best way to explain it is through an example, and the Gaussian universality is one of the most well understood example of that. And as I said, this is very well understood, and what I said only scratches the surface of what is understood about this Gaussian universality class. So we stated this basic hypothesis of independent and identically distributed, but it turns out that it's not really needed. So the condition of identical distribution can be relaxed by a lot. This is what is known as Lindeberg-Feller CLT. So CLT is for central limit theorem. I don't know if I said this before. And independence can also be somewhat relaxed as long as the dependence between the xi's is somewhat weak, in some sense that I will not explain. Central limit theorem still holds. And even more sophisticated results are available. So one of which I can try to explain. So again, it's the same setup. Now just for simplicity, I assume mu equal to 0 and sigma equal to 1. So these xi's are mean 0, variance 1 random variables, IID. Then I look at this partial sum sequence. And then I look at the scaled partial sum. So for t between 0 and 1, I look at the value s of nt. So of course, nt is not an integer, so I just look at the integer part of nt. Then I scale by square root n. So this is now a function. It's a function of t between 0 and 1. It's a random function. And what one can show, this is this famous Donsker's theorem, that this random function under an appropriate topology, which again I will not go into, converges to the Brownian motion. Again, this probably will be familiar to many of the students of science disciplines. So it's a stochastic process. It's a random function. It's a continuous random function with a certain distribution. It's again is very fundamental. It's one of the most fundamental stochastic processes that is used extensively in many natural sciences. So this Gaussian universality, it's not just the central limit theorem giving you rise to the Gaussian. It's a sort of a much richer class, which I do not really have the time to go into, but this is quite well understood. Okay, so this is sort of one of the first example of universality that I wanted to discuss. But again, Gaussian is very well understood and it's everywhere, but it does not cover everything. So not every kind of universality that you will see in nature can be explained by this Gaussian behavior. So there are many other important examples of universality classes beyond the Gaussian one. So in the remainder of the talk, we shall discuss two such examples. One is a large random matrices, and the other one is a two-dimensional random growth. So let me start with the random matrices. So what is a random matrix? Okay, so a random matrix, as the name suggests, it's a matrix whose entries are random. So it's typically going to be a large dimensional matrix whose entries can be real valued or complex valued, but they are random variables. And they are important in physics, in statistics, in numerical analysis, in many other areas of science, not only in probability theory. So people have been studying random matrices for almost 100 years now. Of particular importance of, what do you study about random matrices? You can study a lot of questions, but one of the particular statistic of interest here are the eigenvalues. So you look at a random matrix, a square random matrix typically, or if you take a rectangular random matrix, you will look at the singular values, but let us just consider like a square random matrix, and you look at the eigenvalues, which are again random variables, real valued or complex valued, depending on the matrix, and you want to understand how are these random eigenvalues distributed. That's one of the important questions in this theory. So this person, Eugene Wigner, he was a physicist, I guess. I think he is a Nobel laureate sometime in 1960s. So he came up with a model of random matrices, which are now called Wigner matrices, which he was using to try and model what are these things called? Heavy nuclei, something in particle physics. So what is this model? We don't go into the physics, primarily because I don't know what he was trying to do really. But the model is the following. So we have a random matrix which is IID which has IID entries except for the symmetry condition. So I will make a symmetric random matrix. All the entries above the diagonal. So if I have xij I bigger than equal to j, they will be independent and identically distributed random variables, real valued random variables with mean 0 and variance 1. And I will fill the lower triangular part simply by reflecting. So I'll put xij equal to xji. Okay, so that my matrix eventually will be symmetric. So this is called a Wigner matrix. So first of all, first thing to notice is that because it's a symmetric matrix with real entries, the eigenvalues will be real. Okay, so eigenvalues won't be complex, and it's not terribly hard, although I won't show you, to check that as n becomes large, the eigenvalues grow like square root n. So if you look at the maximum eigenvalue or the minimum eigenvalue, it grows something like some constant times square root n, and in the negative side some minus some constant times square root n. It's not too hard to actually see this. So what one typically does is that one scales the matrix, so the eigenvalues remain bounded. Okay. So what one does is that we take this Wigner matrix, divide it by square root n, or you can simply just take IID random variables with mean 0 and variance 1 by n. And then I look at these real random variables, real eigenvalues, lambda 1, lambda 2, lambda n. Since they're real, we can order them. So lambda 1 is the smallest eigenvalue, lambda n is the largest eigenvalue. And then, you want to understand how do these eigenvalues look like. So the whole distribution of eigenvalues. So how does one quantify such a thing? So there are ways to do that, but the way it is typically done is via this empirical distribution. So I simply consider a probability measure, a random probability measure, which puts mass 1 over n at the location of each of these n eigenvalues. Okay. So of course, I have not said that lambda I cannot be equal to lambda j. So it is possible that at some lambda I put mass 2 over n because two eigenvalues happen to be equal. But I just put mass 1 over n for each lambda I. So that gives me some random probability distribution. And then the famous result, which is nowadays called the Vigyan semicircular law, although Vigyan did not prove it in this form, this was a much refined version, which was proved maybe 30 years after Vigyan. But the result states that if we look at this empirical distribution of eigenvalues, that is this random probability measure, as n goes to infinity, they converge. Again, I don't explain what exactly it means for a random probability measure to converge to another probability measure. But if you know it's like weakly in probability or weakly almost surely, you do not have to worry about what it means if you do not know. But the result says that these distribution of eigenvalues converge to a deterministic distribution, which is given by the semicircular law. So I will probably just show you this picture. So this is a picture I have copied from Wolfram Math World. So this is a histogram plot of eigenvalues of I don't know, probably 200, so 2500 by 2500 Vigyan matrix. So as you can see, the plot is, and they did not scale. So they are just looking at IID entries with mean 0 and variance 1. So if you want to compare it to our picture before, you should scale everything by 50. So what happens is that so 100 becomes 2 and minus 100 here becomes minus 2. So the scaled eigenvalues histogram, they look like a semicircle. Now that's what it's called, a semicircular law, although it's actually a semi-ellipse, not really a semicircle, but the name stuck. So it is between -2 and 2. So the eigenvalues, typically most of the eigenvalues will be after scaling between -2 and 2, and within -2 and 2, they will be distributed according to this density, which is 1 over 2 pi square root of 4 minus x square. Okay, so this is known as the Vigyan semicircular distribution. And again, the important, okay, so let me tell you, if you did not follow what it means for this empirical measure to converge to the semicircular distribution, what it means basically is that for any bounded continuous function f, if I look at the average, if I look at the linear function of the linear statistic summation f lambda I, and I divide by n, then it converges to, so this, the left hand side you can think of as the integral of the function f against the random probability measure, the probability distribution of eigenvalues. So the integral of f against the eigenvalue empirical distribution converges to the integral of f. By the way, there is a typo here, so there should also be an fx. Sorry about that. So the right hand side should be fx times this quantity. So this is just the density of the eigenvalues, and then I integrate the function f against the density. So maybe let me correct it. Okay, so this is what it means for the eigenvalue distributions to converge to a semicircular law. Again, the important fact is that it did not matter what exactly were your distributions of the entries. So all we assumed was that my xij, which are the entries of the random matrix, they were IID except for the symmetry part, and they had mean 0 and variance 1. So this is again another example of universality. So the semicircular law is universal limit of eigenvalue distribution of symmetric Vigyan matrices. Okay, so this is one other example of universality, and this is not the only one. I mean, random matrices universality is again very rich, and although it's not as well understood as the Gaussian universality class, it's still pretty well understood. So one other example I want to talk about is the case where it's not symmetric, or not Hermitian, if you will. So now I will simply take an n by n random matrix with IID entries, which are possibly complex valued. Since I don't impose a symmetry condition, now my eigenvalues are no longer necessarily real, so they can be complex. So these IID random complex valued random variables with mean 0 and variance 1. So variance of a complex valued random variable is simply with mean 0 is simply expectation of mod z square. So again, it's typically of order square root n, and now you look at the eigenvalues of xn by square root n. Again, they're no longer ordered because they're in the complex plane. So this is the typical plot of eigenvalues that it looks like this. Again, the picture is stolen from Wikipedia, and you can see pretty much it's distributed within the unit circle, and it seems like pretty much uniformly distributed within the unit circle. This is probably 1,000 by 1,000 if I remember correctly, the simulation. So, and actually one can show indeed that for this case, the empirical distribution of eigenvalues converges in probability to the circular law, which means that it converges in probability to the uniform measure on the unit disk. Okay, so this result is called the circular law. Again, so I have put pictures of Terry Tao and Van Fu, who were the one to obtain the final version of the results, but this actually has a long history. You know, starts with people like Jirko and Bai, and with people like Erdos Yao and a lot of other people contributing to it. Just put pictures of Tao and Fu because they were the first one to prove the final form of this result. So this is another example of universality. Again, I did not assume anything on the random entries. I just assumed that they have some mean 0 and variance 1, and then I got this uniform distribution on the unit disk. This is called the circular law. This is again another example of universality. So there are many other aspects of universality in random matrices which are well understood at this point, which I don't want to get into, but if you are interested, I'll tell you some of the aspects, just the names. So first of all, we don't have to look at the full eigenvalue distribution. We can look at, say, the largest eigenvalue. So this leads to what is known as H universality in random matrices. You can also look at the local law. Instead of looking at the full distribution, we look at the distribution of eigenvalues in some small interval or in some small ball. You can look at the gap statistic. You can look at what are the gaps between successive eigenvalues and things like that. So the universality of these things are pretty well understood by this point. It's a very active area. Most of these questions have been settled over the last 10 years or so. The Tao result was probably from 2008, like 15 years ago. So this is still a very active area of research. A lot of work is going on. Although many of the interesting questions has been settled, many of them are still open, and a lot of interesting work is going on in this aspect. Okay, so this was the second story that I wanted to tell you about. So maybe it's again a good time to take a breather and see if there are other questions that need to be answered.
So, Riddhipratim, there is one question by Shashank. How do we quantize universality? I think he wants to ask, how do we quantify universality? Shashank?
Yeah, okay, that's again a hard question to answer, because as I said, universality is kind of a physics term, so it's not really very easy to answer in a math way. But so okay, so if you ask a physicist how do you quantify, how do you know that two things are in the same universality class, most probably they will say that you look at the scaling exponents. So for example, the Gaussian universality, it's characterized by this diffusive exponent half. So you look at the fluctuation square root n. In the random matrices, I did not talk about that. So in the edge universality, it's characterized by a different exponent. So if you go into statistical mechanics side, in percolation, universality is characterized by scaling exponents of different quantities and things like that. So it's it's not something I can tell you very precisely, but one knows once one looks at enough number of examples. But yeah, it's I do not know how to say this very precisely. Yeah, so
Then
what?
Sachin has a question. He's asking any example of where the random matrices are being used.
Yeah, okay, so I did not say it, I guess, the details. So one example, okay, as I said, so there are these examples from physics which I don't understand very well. Like maybe I can tell you a little bit about an example of from numerical analysis. So as you know, this inversion of matrices, they are particularly important problems in computation. So it's particularly interesting for you to, again, so inversion is a complicated business because you're dividing by determinant, and you cannot store arbitrarily precise real numbers in a computer. So when you divide by determinant, if your determinant is very small, the computer might tell you that your matrix is not invertible. So it's particularly important to understand in numerical analysis that suppose you are given a matrix which is invertible, but then for whatever reasons, maybe for computational whatever computational constraint or something, you cannot store it exactly. You have to store like a perturbed version of the matrix. So the entries changes slightly. So what is the chance that this random matrix, this random perturbation, if you assume some sort of model of this perturbation, which is stochastic in some sense, and you want to understand, what is the chance that this matrix that was originally invertible after this random perturbation becomes non-invertible. So I cannot actually invert it. It's an important question to understand in numerical analysis. That's one example. There are many other examples, it's used in statistics, in a lot of multivariate statistics. It's used in many different disciplines. I'm not even aware of all the uses, but it is used in many different contexts. Was there any other questions?
Yeah, Rukmini has one question. Wigner's circular law, does it mean symmetric functions of eigenvalues will follow the circular law, trace, determinant, etc.?
So okay, so what it means is that if I take a function, I take any function f of lambda I, say I look at the sum of f of lambda I, okay, any function f. So if you take f is the identity function, you'll get back the trace. Then sum of f of lambda I divided by n, actually as n goes to infinity, will converge to the integral of f against this uniform measure. So indeed, for trace, you can write it, trace, you can simply write it as summation lambda I, right? Okay, although, so, I mean, one needs to work a little bit extra because just the definition of weak convergence will give you that integrals of bounded continuous functions converge. So identity function is not quite bounded. So you need to work a little bit extra, but essentially, yes, under certain assumptions on the functions, you can get the functions integral of the functions against the eigenvalue empirical measure converging to the integral of the function against the uniform measure on the disk. Was there anything else?
That's it.
Okay, great. So maybe we can move on to the final story of this talk, which is of two-dimensional random growth. So for this, recall the central limit theorem. Okay, so so we're looking at previously this quantity Sn equal to summation xi. One can interpret this as a random growth, a one-dimensional random growth model. So assume that xi's are positive. Okay, so assume that xi's are positive, and so you can think of a column which at time 0 has height 0, at time 1 had height x1, time 2 has height x1 plus x2, things like that. And so Sn is simply the height of your column at time n. So you can think of it as a randomly growing column in one dimension. And the Gaussian universality explains the large scale behavior of this randomly growing column. But as you can see, it's a far too simplistic model to be of much use in any real naturally occurring situations. So what we will consider is a two-dimensional model of growth, which incorporates some of the more natural aspects of how growing columns can interact with one another. So let me give you an example. Yeah. So we'll be talking about two-dimensional growth models. So we'll take the two-dimensional lattice, and at each point of the lattice, at the point ij, I associate a random variable, non-negative random variable, say xij. And so how will I define my growth model? I'll take a path that starts from the bottom left corner, and it moves either up or right. So this, like this red path in this figure. And I'll calculate the weight of this path, if you like, as simply summing the random variables on this red line. So I look at x11 plus x12 plus x22 plus x23 and so on. So I sum this. So for each path, I have a sum of these random variables, exactly like before. So these are IID random variables. So for each path, I have a sum like in the central limit theorem. But what I do is that I don't look at this value for a single path. What I look at is a value of maximum. So I fix a point. I look at some point in the, say, n comma n or x comma y if you want. I look at this sum over a path connecting the bottom left corner, which is 0 comma 0 to x comma y, and then I take maximum over all such paths. Okay, so this is it's a random growth model as before, but it incorporates the interaction between different columns. So this is a model, it's called a last passage percolation. So this picture shows, so this blue region in the picture is the set of all vertices V such that the last passage time, this statistic Txy is less than equal to T. So V is a point xy such that T of x comma y is less than equal to T for some large T. So that's why it's called a random growth. So at time T, you can think of it as like, so this is the cluster of growth at a time T, this blue region. This is a model of planar random growth. This is, it's actually quite natural model, which I do not have time to explain to you why, but this is called the last passage percolation model. It's around from 70s and it has a lot of motivation. I guess originally it came from biology. This type of model, like model of bacterial colony growth and things like that. There are also lots of connections to statistical physics. So the important statistic you can look at is that this quantity Txx, Txy that I told you about. We'll not talk about all xy, although we can, but let us just look at the diagonal direction. So we'll just look at T of n comma n. So you look at so you interpret the T of n comma n, you should interpret it as the height of the column, going back to the previous analogy, height of the column at location 0. That means that you are looking at the diagonal line x minus y equal to 0. You should think of it as the height of the column at location 0 at time n. So it's a two-dimensional growth. Remember, this is a two-dimensional growth. So you picture this. You rotate this picture 45-degree anti-clockwise. Then the line x equal to y that becomes the line x equal to 0. So I have at time n along this line, I define the height as t of n comma n. That's the analogy of the one-dimensional growth model that I talked about before. So as I said, so there is a maximum. The quantity t n comma n is defined as a maximum. Each term inside the maximum is still something like the previous central limit theorem that we encountered. But now we look at a maximum of many such quantities, and most importantly, these quantities are not not independent. So if I take two different paths which intersect at some point, then of course, when I look at the quantity, the sum from corresponding to these two paths, they will both contain the same random variable. So they will actually have some sort of dependence. So that's what makes this model much more difficult to, first of all, much more realistic to model many real life situations, and second, much more difficult to analyze. So one can check, not too hard to see that the growth is still linear, like the previous case where it was n times mu. So you can show that the height at time n is still growing linearly with n. But the fluctuation, which was previously square root n in the central limit theorem, it is no longer the case. It is no longer square root n. But it is predicted still that the fluctuation will be universal. So no matter how you have chosen your xij's, the underlying noise variables, the fluctuation will still be universal. That is predicted. But the difference in this story compared to the previous two stories that I told you about is that this one is open. So it's not settled yet as mathematically. So there are physics conjectures on what should happen, numerical simulations suggesting that indeed that should happen, but mathematically we don't know that it happens. So let me tell you the story a little bit here. So this three physicists, Kardar, Parishi, and Zhang. Parishi, you may have heard, he was a Nobel laureate in physics in 2021, a couple of years ago. They are all three of them are famous physicists. So in 1986, they came up with a physics argument to say that models like the last passage population, and many other models, their large-scale behavior should be universal and governed by what is now known as the KPZ equation. I won't go into that. We don't have time for it. But they argued, they provided some physics heuristics, which indicated that the fluctuation, the fluctuation of the random variable t on n comma n, instead of n to the half, it should be n to the 1/3. And this matches the simulation results. Okay, so now then we should ask this question maybe that why do physicists care? This is since that was 1986. It is like 37 years, and this area really have exploded both in physics and in mathematics. So why, one should ask, why do physicists care for such models? So one thing is that the models are simple to describe and easy to simulate. So you can do a simulation and actually see what is happening very easily. And more importantly, even though they are quite simple to describe, the large-scale behavior simulated or predicted for these models actually match quite closely to experimental observations in many naturally occurring systems of stochastic growth. Let me give you some examples. So this is a picture of mutant bacterial colonies that are grown in a petri dish. And if you look at the edge of these colonies, the fluctuations there is expected to match, or at least empirically matches the fluctuations in this predicted by KPZ. This is another experiment, results from another experiment about like how when you burn a paper slowly, you'll see that there these lines form which are kind of jagged. And what do the fluctuations of those lines look like? Again, empirically, this seems to match the KPZ prediction. This is something in crystallography. I don't really know what exactly this is. So there is some phenomenon they call dynamic scattering modes. And then if you look at the interface between two dynamic scattering modes, that again looks like a rough surface, and the fluctuations of those surface, that again numerically matches the KPZ predictions. This is a particularly nice example. So this is about like when you spill a drop of coffee on a piece of paper and let it dry, then it forms like a circular or elliptical coffee drop. And then if you look at the edge, it's not exactly smooth. The edge is kind of, again, jagged. And under certain, so if the colloidal particles in your coffee are ellipsoidals, then it turns out that the edge of this dried drop of coffee, again, empirically that matches the examples of KPZ. So there are at least empirical evidence that this universality class that these people this Kardar Parishijang postulated, it seems to match many real life examples. So that's one of the reasons physicists are very excited about this. They have been very excited about this for the last almost 40 years. But I'm not a physicist. I'm a mathematician. So why do I care? But before that, I'll just show you this fun picture. I don't know if among the younger audience, probably you have never seen this game. It's a quite popular game in the 90s. With this handheld consoles. It's a game of Tetris where you have this tetrominoes falling, and then you have to sort of move around and like let them fall in the empty spaces so that the whole thing is not covered up. So whenever it gets stuck into some column, then it cannot move down any further. So even that game of Tetris, some version of this game of Tetris actually follows this. It seems to follow this pattern. I'll show you this GIF from this person, Martin Thomas. Let me see if I can open it. Yeah. So this is, these are this tetrominoes falling, and you see how this interface is growing. And this, if you look at the top envelope of this interface, then again that it turns out, at least empirically, that matches this KPZ fluctuation behavior. Okay, so maybe I have convinced you that this is something interesting, but why do mathematicians care? So primarily, why we care is that the problems are very hard. It's extremely hard, and there are many surprising connections to other subfields of probability and other different areas of mathematics, like random matrix theory, partial differential equations, representation theory, algebraic combinatorics. So there are lots of surprising connections to these models to many other interesting areas of mathematics in general. And as I said, unlike the previous two stories, the question of universality is completely not settled. It's not quite understood rigorously. And we all love to solve problems that are hard to solve. So what have people been doing in this area? So there is this this phenomenon often referred to as the KPZ revolution, which refers to the explosion of research over the last 25 years on a handful of model of, say, something like last passage percolation. So the question of universality is not understood yet, but we can still pick and choose specific models in this class. So for example, we can pick and choose one particular distribution of Xij in the previous case and see if we can say something about those models. So indeed, actually, it happens so that you can pick some special distributions for which you can say a lot of those things. And these are called the so-called exactly solvable models, because for these models, you can quite magically map the question of understanding this quantity T and N to a different problem in another area, sometimes in algebraic combinatorics, sometimes maybe in complex analysis, maybe some predominant problem or something like that, which lets you write down an explicit formula, although very complicated, but explicit formula of the distribution of that quantity T n comma n. Okay, so a field in probability, a subfield in probability theory called integrable probability has emerged over the last 25 years, where people try to find such magical bijections and associated formulas and try to analyze those formulas and see if the analysis matches what the prediction of KPZ is. And indeed, some progress, a lot of progress has been made over the last 25 years. So I'll tell you only one example of what happens. So you can take the xij's to be an exponential random variable, which means that they're positive and probability that it is larger than some positive number x is like e to the minus x. And this model is important because it's connected to statistical physics. For those of you who have some physics background, this is connected to the asymmetric exclusion process. So in that particular case, you can work out explicitly this limiting distribution of Tn comma n. So if I put x equal to y and x equal to 1 and y equal to 1, then Tnn grows like 4 times n. So Tnn by n goes to its limit is 4 almost surely. And one can show that if I subtract off this 4 times n and divide by this n to the 1/3, which was predicted by KPZ, times the constant 2 to the 4/3, then it converges to some non-trivial limit distribution f. So this result should really be compared to the central limit theorem. So remember, in central limit theorem, I had this Sn minus n mu divided by sigma square root n, where mu and sigma was dependent on the specific model, but n square root n and the normal distribution was not. So it's exactly the same. So this 4 and 2 to the 4/3, they are specific to the exponential LPB model, the exponential last passage population model. But it is expected, but not rigorously known, that this n, well, n part is rigorously known, that if I subtract off some constant times n, divide by some other constant times n to the 1/3, it is expected to converge to again the same distribution f. So for the special case of exponential LPB, we know this rigorously, but it is believed that under pretty general conditions on the distribution of these xij's, a result of this kind is expected to hold, just like the central limit theorem. But this is not quite the central limit theorem because the fluctuation is n to the 1/3 and not n to the half. And also f, the limit distribution here, is not Gaussian. It is quite different distribution. It's called the GUE-Tracy-Widom distribution after these two mathematicians, Craig Tracy and Harold Widom. It's a complicated distribution, which I won't talk about, but let me just mention that this Tracy-Widom distribution, it actually first did not arise in this context of this random growth model. It actually arose as a universal limit distribution for largest eigenvalues in random matrix theory. So remember, in the random matrix theory, I told you that there is also a universality for largest eigenvalues. So there also, if you center and scale properly, the largest eigenvalue converges to a limit distribution, and it happens to be the same distribution that the passage times in the random growth model, the two-dimensional random growth model, are expected to converge to. There are some deeper connections to random matrix theory, which I don't want to get into. But the point I want to make is that these things are all rigorously known for that specific model, exponential LPB, because the exponential model is special. It's exactly solvable. We can write down exact formula for those models. But qualitatively, all those results are expected to be true for a much more general class of last passage population models. It's predicted that the same fluctuation behavior holds, for example. But this question remains wide open. So we know it for exponential. We know it for a handful of like 3 or 4 other examples, which are again exactly solvable because you have this magical mapping to some other problem. But it is believed to be true universally. But the universality question is wide open. We don't know how to solve it. Okay, so this remains. So this is again one of the very active areas of current research. Many open questions, a lot of things happening, but many of the major questions are still open. So just to summarize what we talked about today is that I hope I convinced you that universality is kind of an important phenomenon in nature and can be understood by many of the somewhat simplified models in probability theory. There are universality classes like Gaussian, which have been classically studied and pretty well understood. But there are others which are topics of active research, in particular the KP's universality, which is predicted to explain this large-scale behavior of two-dimensional growth models, where the rigorous understanding is quite limited. It is limited to these exactly solvable models to a large extent. All right, that's all I wanted to say. So I thank you all, and I'm happy to take more questions.
Thank you, Professor Basu.
Yeah, thank you Riddhi, so much for this wonderful talk where very hard things are explained so simply. Thank you so much. So now the floor is open to questions.
So was there any question in the chat that we hadn't?
Yeah,
I think Rukmini had a question. So Professor Rukmini, please go ahead and ask, and I'll ask other
yeah, so I
participants to
was
raise their
asking,
hand.
yeah, so I was asking about like, you know, boundary of clouds. They also have fluctuations and fractals. I guess they are called fractals. So have people also studied
This
distribution?
actually I don't know. So for example, but there are examples. So for example, you know, forest fires.
Okay.
So if you look at the boundary found by the regions burnt in forest fire, that appears to have the same thing. So there are many other natural examples, but the clouds I haven't seen. It's possible
Okay.
that people have looked at it, but I do not know.
But they are not KPZ, right?
No,
Forest
these
fires?
forest fires are, I think, actually believed to be the KPZ
KPZ.
class, but the clouds I don't know. I haven't seen this this
So
cloud.
please raise your hands, and there are probably other questions in the chat box.
Were there any other questions in the chat box that?
So please recommend. Oh, first of all, sir, why black holes have high entropy? Next was please recommend some resources for further study.
Well, I'm clearly the wrong person to ask the question about black hole. I have nothing to do with black holes. So, you know, there are many in ICTS who are expert in this area, but not me. So I cannot answer that question. But what was the other one?
Any further resource material for further study?
Okay, this is hard to say without knowing, you know, what the background of the person who asked this question is. But if you're interested, you can feel free to email me. I mean, I
Some
cannot
very
say.
basic books where even central limit theorem can be found, something like that.
So central limit theorem can be found in any undergraduate probability textbook. So it's for graduate level, if you're specializing in probability, so topics like population. But okay, so Shashank, are you from physics background or from maths background? Okay, so if you're from physics background, then I'm not sure what to recommend to you. But if you are interested in learning like the mathematical theory of population, there are classical books by Grimet, or you know, there are many lecture notes available online these days that you can look at. But if you are trying to understand the physics perspective of population, I really am not the right person to suggest some resources. I do not really have much understanding of that side. Okay,
If you have
so
further questions, you can put your hands up and we will unmute you.
So, Professor Riddhipratim, there was one question that you said you will attend to at the end of the talk.
right. So this was this question about this maximum, right?
Yes, by Srinivasan Ravi.
Right.
The question was, the sum is bounded above by the maximum and below by the minimum. Why this inequality was not considered for the partial sum initially? Any idea?
So first of all, sum is not upper bounded by the maximum or lower bounded by the minimum. You can say sum is upper bounded by n times the maximum and lower bounded by n times the minimum. If I don't know if that's what you meant, but the point is that you can look at this upper bounds and you can study the maximum and the minimum separately, but that doesn't give you the right result. So if you look at what is the limit of the maximum or n times the maximum, you will get something. It's possible to do that. But that will not be the right answer of just looking at the sum itself. So if we want to understand the sum, it's better to look at the sum directly. Of course, if we cannot look at the sum, if we cannot analyze the sum, we can look at these different bounds. But for this particular case, one can actually analyze this maximum and minimum of the this IIT random variables, but those have very different behaviors than the sum. So it's not particularly useful to look at those.
Okay.
So there's still any questions? Have we dealt with all the questions in the chat? And there is a hand I see.
Okay. Yes, I see. I'll unmute them. Just give me a moment. Yeah. Ishan.
Yeah, I had one question. What exactly do you mean by fluctuations here? Like fluctuations as in like fluctuations in the clouds and all. I don't understand what that exactly means.
Okay, so right. So you mean in the question of in the context of natural sciences, like fluctuation of an interface. So fluctuation in the cloud.
You said that the KPZ equation that governs these fluctuations and all. So what does that exactly mean?
So it's a right. So you can think of these. So for example, I don't know if I go into this picture, probably is easier to understand. So you look at these interfaces. They're coming from some experiment. Okay, so you can, the same explanation holds for clouds or forest fire or whatever other things that you want to understand. So this surface is a rough surface, right? And it's also a stochastic surface in the sense that if you did the same experiment again, you will not get exactly the same interface. You will get something that looks like the same. So one way to look at the fluctuation is the following. Say, if you look at, you fix one particular point in this interface, like, I don't know, let me see. No. Say here, no, say this line. And you ask, what is the height of the interface? At which point does this line meet the interface? And if you do different experiments, you'll get different points. So these are random observations. You can talk about fluctuations of a set of random variables, right? I mean,
right.
In principle, okay, you can measure them by standard deviation, but you can talk about fluctuations in general. So in that sense, or you can look at like two different points, and then you ask, so what is the difference between the height of these 2 points? So if this distance is some number t, how does the difference, the typical difference between the heights at these 2 points, how do they behave as a function of t? They'll be random, but maybe they grow like some power of t times a constant times a random variable. So that's what I mean by fluctuation.
Okay.
Okay, I think
I'll unmute Ruchi.
Yes, sir. There was an result on your slide that for any bounded continuous function, 1 over n summation f lambda I goes to some integral minus 2 to 1 by 2 pi root 4 minus x square.
Right. So let me that slide again. Yes, this one you're talking about, right?
Yeah. So if I consider the where this function, this summation goes to, so this is approximately maybe, if I'm not wrong, this right hand side where it is converging, it is a one. It is nearly one. If I'm solving this integral.
No. So if you do not have this f, if I said already that there was a typo. If you did not have this f, then this
So this
integral.
this fx is where? This is fx over 2 pi.
Yes. So, so if I did not have this fx, if I just look at this integral, then it will be exactly equal to 1, because this is the probability.
Yeah, this is exactly 1. Yeah.
Probability density integrated is always going to give me 1. But what is the correct thing is that this times fx. This is the integral. So what you should think of is that this is the integral of f against this density.
Okay. One more thing. So this is one summation. So we have n eigenvalues, right? So value of function on those n eigenvalues over this n. So what does this mean over this n? So is it the average?
Yes, exactly. So this is like average. So you should interpret the left-hand side in the following way. So I have these random eigenvalues, right? Lambda 1 and lambda 2, lambda n. So there are n eigenvalues. I pick one out of them n as random, at random. So each of them I pick with probability 1 over n. So then this quantity is simply the average. I pick lambda 1 with probability 1 by n. So I get f lambda 1 times 1 by n. I pick lambda 2 also with probability 1 by n. So I get another f lambda 2 divided by 1 over n, and so on. So the left hand side is simply the average. So given the lambda i's, so once I fix the lambda i's, I look at the average value of f over those lambda i's when I pick one of them uniformly with probability 1 over n. So that's how you should interpret the left hand side.
Okay. Just one more.
Yes.
Okay, so this lambda is what kind of lambda is these are? These are random eigenvalues, or these are eigenvalues generated or made by some linear operator?
It is eigenvalues of a linear operator that itself is random, right? So this is my model, right? So I have my linear operator. This is x is my linear operator, where the entries of this matrix, they are random. So the linear operator itself is random. So when I look at the eigenvalues of a random linear operator, then they are also random.
Okay. So can this result help in solving this the summation of some functions over some if we have a linear operator and particular eigenvalues, so can this convergence help us to solve this average?
I did not quite understand what you mean. So solve what? So see the right hand side, I know I can compute exactly. The left hand side is something random. Okay.
Yeah.
So what it can help me is that without looking at the distribution, if I only wanted to evaluate this quantity for large n, then I can simply approximate it. So the left hand side is random. To evaluate it, I have to generate eigenvalues, generate the random matrix, evaluate the eigenvalues, and so on. But this result simply is telling me that, okay, there is no need to do that. If f is bounded on continuous function, if you only want to know what is the average of f over your eigenvalues, if n is large, then you can well approximate it by the integral on the left hand side. So I did not quite understand what what you meant by solving a certain summation, but this is what it means. So you can the right hand side you can compute directly given the function f, whereas the left hand side is a random variable which depends on the particular choice of your sample of the entries of the random matrix. What this result tells you is that with very large probability, if n is large, the left hand side is actually close to the right hand side. So you can approximate the left hand side by the right hand side for n large. That's what it means.
Okay. Thank you, sir.
Okay. Yes, Rukminidhi.
Sorry, I was. Can we go to your slide when the lambdas can be complex?
Yes, sure.
Yeah. So again, what exactly is the distribution to which it's converging? Is there a
It's just the uniform distribution on the circle. It's just the dx by 2 pi. So dx by pi, that measure.
oh ds by? But
Sorry,
is
that
there any situation in which it goes to say some other volume measure on the unit
oh,
d?
yes. I mean, you can. So this is specific to this IID case.
Yes.
It's
Yeah.
not like So, for example, this semicircular law. It's also for IID. If you change the matrix structure. So, for example, if you had a random Toeplitz matrix,
Okay.
it would converge to a different limiting distribution.
I
If you
see.
change
Yeah.
to a random circulant
But
matrix,
what I mean is, do on the right hand side, does the geometric volume measures ever come of?
yes, they
Okay.
do. Yes.
Okay.
I mean, they
Okay.
do, but uniform measure is also a kind of volume measure.
Yeah, that is true. Yeah.
So different volume measures do come, but
For
this one
example,
is
the measure on the sphere, the volume measure on the sphere, does it ever come?
yeah. Okay. So yes, I mean, but not in the IID case, because in the IID case there is no. So for example, if you look at like the random, I forget, but if you look at the random unitary matrix, for example,
Okay.
there the eigenvalues would be on the unit sphere, I suppose, on the unit circle, I suppose. But I forget what the distribution looks like if you look at the Haar unitary. So there are, so in the IID case, there is nothing forcing your eigenvalues to take absolute value 1 only, right? So if you want the measure of the circle, you first have to make sure that your random matrix takes eigenvalues only on the or close to the unit circle.
Yeah. Yeah.
So yeah, again, I mean, this is not
I
really.
suppose it can be realized some way. Yeah.
I mean, I'm pretty sure these things are known, but again, random
Yeah.
matrix is not really my specialty, so I cannot say off the top of my head.
Okay.
But there are examples for example, there are examples where you can make the distribution on the circle just by taking, say, the Haar unitary random matrix. But if it's, and then maybe it has to be uniform because it's rotationally invariant. Maybe I forget. Probably that is true. Anyway, I don't want to claim things that might not be correct.
Yeah.
But yeah, so here IID uniform is specific for IID. If you change the structure of the matrix, then the uniform distribution need not hold. As I said, in the real case, where you have this semicircular law is kind of specific to the IID symmetric case, the Vigyan case. There are other models of random matrices like Toeplitz matrix, which is just the Toeplitz operator, but now you look at the entries are random. There it's a different law. There's something called circulant. There it's a different law. There are different kind of limiting spectral distributions that you can get by changing the structure of the matrix. But as long as the structure remains IID, then you get the
uniform distribution. I see. Thank you. Very nice.
Yeah, there are no further questions. So, Rukmi ma'am, you can, if you have any comments, you can go ahead.
Yeah, no, I just want to thank Riddhi for this wonderful talk. And yeah, we got a very good glimpse of the subject. And yeah, hope some people will be enthused to ask a lot of questions, and maybe through outreach email, and we can forward it to Riddhi maybe.
Sure.
Sure. So, if people are interested, they can write to.
Okay, great. Thank you so much.
Thanks.
Thank you very much, Riddhi. Yeah. Okay.
Yeah, thanks. It was a pleasure. Okay. Thank you. Yeah. Bye.
Thank you.